Hi, my name is Shady. I am presenting our work on image restoration using deep projected GSURE. Inverse problems appear in many image processing and computer vision applications, where the goal is to reconstruct a latent image X from its corrupted version Y, which is observed using the following measurement model, where the measurement operator H can be expressed as an m by n matrix and E represents an additive Gaussian noise. For example, when the operator H is a blur operator, the inverse problem is referred to as deblurring. When H is an anti-aliasing filter followed by subsampling, the problem is referred to as super-resolution. In many cases, image restoration problems are ill-posed. Therefore, fitting the least squares loss and relying only on the fidelity term usually results in poor reconstruction. As a result, one needs to add another prior assumption on the reconstructed image. Formally, we add a regularization term to the loss. In the more general case, we replace the least squares term with the general loss function L. In this work, we propose to replace the least squares loss with a more sophisticated term called projected GSURE, which is an unbiased estimator of the true MSE projected on the range of the measurement operator H. Let U be the input of the estimator X hat, which we assume is a sufficient statistics for estimating X. Then, the projected GSURE is given by the following expression, where C is a constant value with related to U. The second term is the norm of the estimated image projected on the image of H. The third term is a correlation between the reconstructed image and the maximum likelihood estimator. And the last term is the divergence of the estimator with related to U, which is given by the following expression. For the considered model, we use the following U and maximum likelihood estimator. Optimizing the projected GSURE directly using gradient descent framework requires evaluating the Hessian of the estimator, which is very complex and requires a massive amount of memory. Therefore, we use the following Monte Carlo approach, where G is a random Gaussian vector with the same size as U, and epsilon is a sufficiently small scalar. In order to be able to use GSURE, we need from the estimator X hat to be sufficient statistics of U. Therefore, we parameterize X hat using a convolutional neural network F with parameters theta. This leads to the following loss function and the following objective function. Although the projected GSURE estimates the projected MSE, we still would like to add another prior term for gaining better results. Therefore, we modify the following objective using variable splitting approach, and then solve it using ADMM, where we use beam 3D denoiser for solving the second step and run the whole scheme for a number of iterations similar to what is done in the plug-and-play approach. We test our method on two types of inverse problems. For deblurring, we test our method on the following 6 scenarios, which include different blur kernels as well as different noise levels. Similarly, for super resolution, we test our method on the following scenarios, which include different anti-aliasing filter and different noise levels. Here we can see visual comparison of the deblurring results on scenario 5. And more generally, we see the results in numbers tested on set 5 and set 14, compared to deep image prior, which is based on least squares fidelity term and standard plug-and-play method. Here we see visual comparison of the super resolution results on scenario 6. And similar to deblurring, we see the results in numbers compared to deep image prior, ZSSR, and standard plug-and-play. These results prove that GSURE outperforms existing methods. Thank you for listening. We have our code available online. Please check it.